Beautiful. All right, so the plan is to, as I stated in the Discord chat, to start with chapter 1 and just go through the entire book, basically. I've got this whiteboard set up. I've got this decent kind of pen writing, digital writing pad thing that I can control it with. Um, what I'm doing is I also have my 8.5 by 12 or by 11, just my normal white paper here. I'm going to be using just to fill in that little note sheet that we can use on the exam, just with anything I think is important as we go along. If anything is super particular, that might be fantastic for that. Yeah, let's do it. For some people, chapter 1 may have been like a super review, but I didn't come from a background where we did the logic gate stuff, and my CS program sadly didn't cover this aspect. So this was definitely something that I had to learn in this class. So I just want to do a quick review through chapter 1. Well, it's 70 pages long, so we'll just move through it and just make some things happen here. So the fundamental unit in a classical system is a bit. Obviously, in the quantum, we're dealing with qubits. We know that. Gates are unitary. That is, they prescribe some type of qubit rotation. Is how I've always taken that to be here. Quantum gates always have to be reversible, which comes into play later. And then just this other stuff here. Honestly, the complexity class stuff is still a little bit beyond me. Bits, the ones and zeros, really standard stuff here. There's 2 impossible states, so if we have 4 coins, it's 2 to the 4, 5, 2 to the 5, basic stuff there. Dice, it's 6, so it's the same thing. 6 to the 4th, 6 to the 5th here for exercise 1.2. Excuse me. In terms of encoding information, this one was pretty interesting. I don't really feel like we need to go too deep into there. Physical bits, once again, not a problem. Binary, straightforward. Most of the stuff that was new to me that was in chapter 1 was down here when we got to gates. So let's do just a quick run through of all these different gates. My goal is to get through chapter 1 in basically the first hour or less, honestly, because there's a lot of stuff that we can just generalize over here. And by the way, can everyone see this stuff okay? Is the quality of the text coming through, or is it looking pixelated? All right, so classic AND gate. A to A. If it's 0, what is this nonsense? This thing is a little janky, sorry. If it's 0, we're going to get a 0. If it's 1, we get 1. The truth table here. It always evaluates to pretty much to what we put in. So if it's false, it's going to evaluate to false. If it's true, it'll evaluate to true. Okay. The more important slides that, like when we go over like some of the more advanced practice problems, especially when we get into the actual quantum stuff, I will be. Why is this? Okay, hang on. This thing is so weird. Christ. I don't really understand why Microsoft Whiteboard does not have an eraser. Why is that not a thing? If anyone knows better about this than I do, please point me out here, because what is this? Okay. Fucking hate it. Why aren't you letting me erase? Am I actually going to have to Google this real quick? Hang on. Click on the eraser icon in the toolbar. Well, that would be wonderful if it existed. Okay, I don't really... Okay, it's letting me do stuff now. Oh, okay. And why is this stuff still here? I don't... Okay, you know what? We're just going to call that Mark 1. Okay, alright, so the AND gate, OR gate, same kind of business here. NOT gate's next. Okay, NOT gate. Negates. Whatever we put in, the opposite comes out. The always 0 and always 1, we didn't have to deal with those. I'm just going to skip over that. So really, you know, what we're the analogs to what we're going to be primarily doing are going to be with the things that work more with the 2 bits and some of these more advanced kind of single qubit stuff later on. So let's jump in here with our AND gate. So A and B basically puts out the conjunction of A and B. So unless A and B are both 1, both need to be 1, we're going to get 0. Let's just put that in there. So A and B are 1. And we get 1. Otherwise, no dice. We got the OR gate. Whatever, that is terrible. Signify by plus. And it's going to put out whether A or B or both are true. So 1 or 0 is acceptable for either of these in order to equate to 1, 0, or 1, 1, or 0, 1 will all equate to 1. Oh, I can even zoom this out. Very nice. Okay, moving on, we have the XOR. Again, I apologize, I am not an artist. I am barely a functional human being. Okay, so it's just A, addition modulo 2 in mathematical terms. So either we're looking for A or B, but not both. Oh, Christ, but not A or B, but not both. And so either A is 1 or B is 1. But if they're both 1, we get 0. Pretty standard stuff there. NAND gate, not AND. It just negates the AND. I don't think we need to go into that into detail. If you guys want to go over anything in a ton of detail, just pop in the chat. I also have the poll feature set up, so if I ever need to do like a group decision about whether to go deeper into something or etc., we can do that. The NOR, which is the not of OR. Again, that looks like a P, but we're okay. What is that? I have no idea what it's doing. All right, not or. So negates the or. Pretty standard stuff. So basically, the only time this will ever equate to true is when A and B are both false. A and B are both both 0. We get 1. Otherwise, 0. Okay. And then, you know, they've got a bunch of other little things here you can experiment with. The negative or, where it negates it before it puts into the OR gate. The negative and, where it negates it before it puts into the AND gate. This is all verifiable with a truth table. Physical circuits, not going to spend a lot of time here. This is all pretty standard stuff. Multi-gates. Okay, so now we're getting into... shit. Alright. What is this nonsense? Dude, I swear this thing is cracked out. And yet these lines remain. So, you know what we're going to do? We're just going to zoom this bad boy out. Or not. Maybe that's not a thing we can do here. Oh. Christ Jesus. There's actually an eraser. But it's not erasing the lines. Alright, you know what? Now that we know there's an eraser, we can just actually use that. Okay. Multiple gates, you know, we can combine things together. Combine an AND, take in 2 inputs into an AND, and feed that into with another bit into like an OR. To get various configurations. So, pretty standard stuff there. All verifiable through truth tables. Yeah, chapter 1 is the one we can float through here, so we can get to the actual quantum stuff tonight. So universal gates. We've discussed this at length in obviously the quantum side of things. Basically the gate primitives, if you will, things that are the gates that are the smallest possible chunks that we can build all other gates out of. So for classical, we've got the not, and or, and so we can pretty much build any circuit using these gates. And there's a process here, Lin Wong, to build this, to go through there and determine that. I don't want to skip through this too much, but I feel like this is not the meat of the matter. Not and or. Not and is also universal. So you can build an or out of nots and ands. NAND is universal. Literally the most universal one ever. So, you can build everything out of NAND gates if you felt like it. Okay, so the adders, I'd never seen this before, so it was useful for me to come in here and take a look at how a classical adder works. So the carry and the sum were concepts that were new to me. So we have the 1 plus a 0 is 1, and 1 plus 1 is 0, and we carry the 1 over. And so we just work our way from right to left, doing that with summing and carrying, and we add two binary numbers. And then to implement that into an actual circuit, we can build the half adder, which is where we'll really start digging in here. So I'll do my best to start cleaning these lines up too, making sure it doesn't look like chicken scratch. Okay. Well, the dot goes here. Jesus. Alright. Again, trash drawings, but we get the picture here. So we're doing the XOR of A and B to get our sum. So if we think about it, if 1 and 0, we want 1. So XOR of 1 and 0, 1 or 0, boom, 1. If we have 1 and 1, well, we want 0. So the XOR will give us 0 for these two values. So essentially we're just, sum is an XOR in the classical configuration here, and then the ANDs are going to give us, this AND is going to give us our carry. So if A and B are 1, both 1, then we get a C, our carry, of 1 by evaluating with the AND. However, if it's 1 and 0, or 0 and 1, or 0 and 0, then we get 0. This is the half adder. This is just one iteration of finding sum and carry. Alright, so then we go into some other stuff here, which we're not going to worry about that right now. The full adder is an implementation. Let me scroll this down. Jesus. Out here. All right. The full adder so I tried the first 2 bits remaining. So is where we feed forward. Jesus, I need to get better with writing. Feed forward the carry bit. So we feed forward the carry bit into the full adder. So that means that we need to, not only are we taking A and B now, which are our 2 individual bits in the position of the 2 bit strings that we're adding together, the 2 binary values, pardon me, but we're also taking a carry in, which will be used in there. So let's work through here according to the diagram. So just draw this in here and explain these as we go. So our sum is going to be another XOR, except this time we'll be taking the values of sorry, that is wrong. What is this? Okay. A and B. just finish drawing this out. Sorry, while I've still got this fresh. See out. And okay, so the XOR of A and B gives us the sum of A and B, and then we bring that up. And did I manage to completely? Okay, so this needs to come up like so. Also needs to come down to here. Okay, into our AND. So A plus B, the XOR here. So we get the sum of A and B. And then we XOR it again with our CN. And that gives us the sum of whatever step, whatever step we're on, factoring in this carry in. To get our new carry out, excuse me, we need to take the our new carry out. We're going to take the result of A and B we're going to OR that with the AND of CN and XOR of AB. Take the AND, pardon me, yes, and what is this gibberish? All right. AND of A and B, ORed with the output of an AND of the carry in and the result of our XOR. So if A, B, and CN are all 1, well, the XOR is going to be 0. The result here, the XOR, is going to be 0. Let's say the CN is 1, so we now have 1 and 1, which will equate to 1. And also, if A and B are 1, then we'll get 1 or 1, which will give us a carry out once it filters down through here, through all this equation of 1. And then the thing is, this just gets fed forward iteratively through sequences. You would turn this into a dedicated circuit, and then just propagate it as many times as you need to. If it's a 5-bit binaries, you'll do it that way, etc. Okay, let's move on. So yeah, the ripple carry is what I was discussing there. So you can either start with a half adder, which will just take the first two bits, the A bit and the B bit there, A sub 0, B sub 0, and then add them together and get the first carry, and it'll pass out the sum and carry, and then that first carry out will feed into the carry in for this first full adder. Or you can just do all full adders and feed in 0 as the first carry in value here for the full adder. Circuit complexity. We're looking at, again, circuit complexity and query complexity is something we'll touch on later in the quantum specific stuff. But it's basically just how many gates are we using to accomplish the problem. So for the full adder, each one has 5 gates, and however many n-bit numbers we have, it's just 5n. So if we're adding a 12, and we're going to need 60 logic gates, so forth and so on. Circuit simplification. Most of this is pretty straightforward. Left to right in order of this should be fairly familiar. Commutative property A, B, and C is equal to AB. A and B and C is equal to A and B and C, and so forth. A or B or C is A or B or C, etc. They're commutative, so we can switch their positions and we're equivalent. And they're also distributive, so we can kind of treat it like a normal thing, like a normal kind of numerical situation where we want to distribute and get products. So A and B or C becomes A and B or A and C. And the same thing here with this guy right here. We can factor this out. Mainly because A and A would be, when we distribute this forward, A and A becomes 0, so it just vanishes, or it becomes 1. This is just another identities here. A and 0 is always 0. A and 1, well, it's up to the value of A, so the result of that will just be A. A or 0 is going to be A. Obviously, so that whole thing hinges on what A is in order to be true, and this will always be 1. Since if we already have 1 here in this OR, it really doesn't matter what A is, right? It's always going to evaluate to 1. Single variable identities. A is just itself inverted twice. Invert it once, invert it again, you're back where you started, right? A is A in itself is just A. A and not A is 0, so they're inverses, so A and not A will always equate to 0. And De Morgan's law, again, pretty straightforward stuff from statistics and logic. I don't really want to go too in depth about this. Circuit simplification might be something, because we look at circuit complexity and query complexity later on, but I'm just going to skip over this. If it's something you guys want me to look at, let me know in the chat. So the concept of, I don't necessarily think we need to go too in depth about how to actually, in a classical sense, build a reversible gate here, but just understanding what the concept is, right? We need to be able to map every individual input to a distinctive output. So this is not reversible because we have, if we get a 0, how are we going to know what the internal configuration here was? And so if we get 1, we always know, well, they were both true, but otherwise we're kind of screwed there. And so we can add an XOR to essentially, well, we see that a little bit later on, but so the Toffoli gate, right, it's a controlled, The FOIA gate is constructed using an and an XOR. So this enables us to basically see to be reversible, because now for every distinct input we have a distinctive output. Making irreversible gates reversible, right? We add the XOR here, and that gives us reversibility in our, because we can literally see it, unfold in the truth table. This is pretty straightforward the way that they explain it in the book. Now, if we've got two outputs, well, then we just XOR with each one using these ancilla bits here. Error correction. Maybe this is a good thing to look over to, because when we move into error correction, but this does not play into anything that we've looked over so far. I know we're moving into that soon. But it's basically we're looking at the bit sequences, and based on the number of bits we have, we can, with a certain probability, determine whether an error or not has occurred, right? So we should all be familiar with big O. I will admit I wasn't really familiar with some of the other ones, but this is all pretty straightforward. Complexity classes. I'm not even gonna try to go over all this NP shit. Sorry, not gonna lie. I'm still a little bit confused about what all this means. The perks of not coming from a math perspective when I got my my CS bachelor's, and really. So the Turing machine, again, cool, but not something that I necessarily think is going to be on the exam. Church Turing thesis, cool stuff, but something that I don't really think is, quantum computational supremacy. Literally, some of the quantum algorithms that we looked at are completely useless. They just exist to prove this quantum computational supremacy. Either, demonstrating something that classical computers would take lifetimes to do with some type of speed up, or etc. All right, so 37 minutes in, beautiful, and we're on to the meat of the matter here, the stuff that we all came for, the quantum realm. All right. So, did anyone buy the Qubit touchdown game? I was curious to know how that's been selling, but all right. Pardon me. So let's dive into the world of the qubit. This is where things get. So we've got our Dirac notation, where we write things with kets. So 0 and 1, for example. These are states, which are positions on the block sphere. More qubit touchdown stuff. So we've got, I'll do my best to, so we've got X, got Y, and then vertically we have the Z axis. So the block sphere has radius 1. And so the states we were just talking about, for example, are the north and south pole in the in the z basis. All right, so superposition. Which is the heart of the matter, shall we say. Superposition is the state can be a combination of different states. And so, for example, they give the Hadamard gate example here. Not the Hadamard, but so basically we have the states 0 and 1 with this given amplitude. Now we know that, well, I won't put the cart before the horse. So if we want to look at other state, we want to move to other states in the block sphere, then we can simply apply a relative phase. A phase should not in this case. I don't know if anyone can even read that. Doesn't impact amplitude. This thing makes my already bad handwriting look even worse. So, for example, we have the same superposition, but we have I here, and that shifts us over to right here. So obviously the use of imaginary numbers are going to continue. So let's say we want to, so that gets us to the positive y-axis. If we wanted to get to the negative, we would just simply do this, but with a minus I. So these states, there are certain states that are kind of, foundational. So they have their own symbols. So we have the plus state, the plus ket. I don't know how you would say that. Oh, the plus. It literally says it right there. So that's our 1 over 2, our square root of 2. Ket 0, ket 1, the minus 1 over square root of 2, 1, the I state, which just gets us to the tip of the positive y-axis, and then the minus I. Alright, foundational states there. You can see here we've got this lovely picture. So 0 and 1 are the poles of the z-axis. The plus and the minus states are the poles on the x-axis, and I and negative I, or minus I, pardon me, are the poles on the y-axis. And we'll see later, but believe that we'll do some calculations of basis state here. So obviously we're not restricted to just being on the equator. We could shift into any position along the block sphere by having different phases. And in terms of they can be in one hemisphere more than the other, depending on our measurement basis. So the cubit can be any point on the block sphere. I'm not going to draw a block sphere and label the following locations. Okay, quick review of complex numbers. Z equals x plus y. So 1 plus I squared root 3. So x in this instance is 1, y is square root of 3. The funky r component, however you draw that. And then the imaginary component, again, this wild looking thing here is y. Okay. All right, so this was new to me. So converting into, it's this polar form. So Z equals RE to the I theta. So let's say we want to convert from one given example. I actually worked through I got these notes somewhere, but I worked through this example on paper somewhere, but I'm not glancing at anything. We're starting fresh here. And then we can also transversely go from the complex back to back from the polar back to the normal complex form. All right, so, and in that case, r cosine theta and y equals r sine of theta. So let's look at the examples of how you can prove this. Geometrically, fine, let's look at that. So your component is mentions the axis. We're in the imaginary axis here. So R, we got theta, x, y. Imaginary axis, and this is the real axis. Okay, so we can find r through the Pythagorean theorem here. X squared of x squared plus y squared, that gives us r. And then with r we have theta. So theta is the inverse tangent of y over x. Yada, yada, yada. Okay. I actually have notes for all this, so this is good. Lower this formula where we say that we can take this and we can bring it over to the complex the complex phase that we wrote and insert it. Which gives us r cosine theta I r sine of theta. So this gives us x, and this gives us our y. So we can take this to x plus iy, which is our complex viewpoint. And obviously it's this here, we can, boom, we take the sum of the squares of the components, we get r squared. I'm not concerned about this. It's trigonometry, right? So stuff that is useful for what we're going to be doing ahead. The complex conjugate. Oh God, complex. So z star equals x minus iy equals, oh sorry, the example is z equals x plus iy, which also equals r e to the I to the imaginary, pardon me, theta. So when we take the complex conjugate, we negate the imaginary part, and then so we've got that is equal to x minus iy, or r e to the minus I theta. The norm, it's just its length. Norm of a complex number z is simply its length r. The norm square, which is its length squared, in this case would be equal to r squared. So we can compute the norm square as well. By multiplying a complex number by its conjugate. These two are equivalent. We can distribute this here with it proves it here. Nothing too crazy, just simple algebra. Distribute everything through, you wind up with the same thing. I'm not too concerned about the complex number stuff. Again, if you guys are feeling something spicy that you want to stick into, just let me know in the chat. But I feel pretty strongly about this stuff personally. All right, measurement. Okay. So let's look at this example they give us here. Again, this phase just has this rotation here, so it basically took it from there and rotated it out. or transversely. Regardless, so it didn't change the position with regards to either of the poles. So to find the probabilities of our each position in our superposition, we're simply just going to take the norm square of of our amplitudes. So in that case, we've got and the norm square of that is 1/2. So we have an equal chance. We have a 50% probability of being in state 0 and a 50% probability of being in state 1. Again, because this example didn't necessarily shift it up or down, it didn't alter the amplitudes. So a phase shift typically in this basis is not going to so probability is given by the norm square of the amplitude. Again, another example that we can see here. This one contains for God's sake, what is this? I'm going to have a talk with Microsoft. We can see, so we've got 2/3, 0, 1 minus 2i, 3 in state 1. So our amplitude squared, or pardon me, the norm squared of our amplitudes gives us the probability for each one. So for this guy, we get 4/9. And obviously the amplitudes must add up to 1. And there's workarounds for when we're constructing a state where that isn't the case. We have to bring in some other factors. So norm square is simply the complex number times the complex conjugate. We wind up canceling a bunch of stuff out here. Minuses get, or the i's get squared into 1s, and they do all sorts of stuff, and we wind up with 5/9. And 4/9, 5/9, 9/9. Perfect. We can do this example really quick just to look at. What are you doing, man? Just let me. For Christ's sake. What is this? Alright. I'll just do one more example here and then we can move on. 2, 3. So norm squaring again. It's the complex times its complex conjugate. So 1 plus I square root of 3 times 1 minus I square root of 3 over 3 squared, which is 9. 2 minus I multiplied by 2 plus I over 9. You son of a bitch. Alright, we'll just zoom out here, add in some extra space. I'm gonna have to get a different whiteboard software. So let's bring this over here. So we wind up, once we distribute, we wind up with Excuse me. One. That's I square root of 3 minus I square root of 3. So we've got I squared of 3 and minus I squared of 3 multiplied together. So it'll give us minus I squared. I squared is negative 1. Just gives us 1. So 1 times the square root of 3 squared, which just gives us 3. So 1 plus 3 over 9, which is 4/9. Similarly, we've got 2 minus I, 2 plus I, 4 minus 2I plus 2I. We get minus I squared, which is 1 plus 1, pardon me, over 9. So we get 5/9. And what do you know? We've got 9/9. So measurement, moving on to measurement. Measurement changes the probabilities. It collapses to whatever state that we have measured it in. So, for example, say you measure the cubit and get 0. What if you measure the cubit a second time? What is the probability of getting 0? Well, the probability of getting 0 is 1. We've collapsed through measurement. We've collapsed the cubit to state 0 with the first measurement. It's not going to change. So 0 is 100% and 1 is 0%. Okay. So normalized, it's normalized if its total probability is 1. Like we're talking about how the norm squares of our amplitudes have to sum to 1. So if that's not the case, then we have to find a normalization constant. So we can work through, let's work through one of these examples here. Let's work through 2.9 together. So we've got a state that is not normalized yet. So, and we need to find A, which will be our normalizing constant. And we've got this E I 6. So the process that we do that is we're going to distribute through our A. So 1 equals, and we'll take our squares here. Plus I might be butchering this. So in order to find the norm square, we take our complex conjugate. Which simply equates to E0. So we have 4E0, this is 1. So we have 4A squared. And over here, we don't need to worry about that. So just double check here. Yeah. We got 9a squared. So 1 is equal to 13a squared. A squared is equal to 1/13, and then we find our square root. So our normalization constant A is 1 square root 13. Let me verify that in the textbook in the answer key real quick. 2.9. So, interestingly, I forgot the phase. Because when we multiply A through, we have to get rid of that. So it's EI theta. Perfect. When we assess those, because we know here that we have 4a squared and 9a squared, we'll wind up with 4 over 13 and 9 over 13 for our probabilities for being in state 0 and being in state 1. I'm just going to grab a couple minutes and I will be right back. We will continue onward. All right, let's jump back in here. So we can measure in many different bases, right? So we can measure in, if this thing will actually let me move it this time without drawing some lines for some reason. Wow, look at that. All right, miracle. Okay. Okay. There you go. All right, so we can measure in, excuse me. So our measurement outcomes are our bases. Basis for singular. So it's essentially the poles that we use to measure in. So our Z basis is 0, 1. So we would measure relative to the poles on the Z-axis for our hemispheres, etc. The X basis measures in our plus and minus state. And the Y-axis, or pardon me, the Y basis measures in the I and minus I basis. So with this example here, we can take we can measure in any different type of basis that we choose. So let's work through this example that they give us, which is square root of 3 over 2, 0, plus 1/2, 1. So if we measure this in the 0, 1 basis, then we're going to get in the Z basis, we'll get the norm square of square root of 3, 2, and the norm square of 1/2. So we'll get 3/4 and 1/4 respectively for 0 and state 0 and 1. But what if we wanted to know if we were going to measure the block sphere probabilities in terms of different bases? So let's say we want to measure it into the X basis, which is, as we just mentioned, plus and minus. That requires a little bit more work. So we know in the X basis that 0 is 1 over square root of 2 plus minus, and 1 square root of 2 plus minus. So we can substitute in the states of our qubits into this. So we've got, square root of 3 over 2, 0. So we'll substitute in this. And for the half, for the one state, we substitute in the X basis representation, which is 1 over square root of 2 plus minus. So we can simply sorry, 2 seconds. Hey, when they leave steps out. Oh, yeah, I apologize. That's simply the plus state. So, square root of 3 plus 1, 2 square roots of 2, plus square root of 3 minus 1, 2 square roots of 2. To get our probability, we norm square it, and this winds up around 93%. I think there was some... yeah, that's right. Sorry, I didn't show the intermediate step where they distributed through and then grouped like terms, etc. But that's how we wound up here with this guy, with these two amplitudes. All right, let's measure in the II basis. So 0 in the y basis. 0 is 1 over square root of 2 negative I. 1 is I over square root of 2 I. So we can follow just the same basic steps that we followed before. We can substitute that into what we have here. Square root of 3 over 2 times 1 over square root of 2 plus 1/2 square root of 2, or 1/2 multiplied by negative I square root of 2 multiplied by Ri minus I. Similar thing, distribute group like terms, and we wind up with 3 minus I over 2 square roots of 2, and square root of 3 plus I, 2 square roots of 2 as the amplitudes for I and minus I. We assess those, taking the norm squares, and we get 1/2 and 1/2. Beautiful. We can also take any two states that are, I forget the term. We can essentially use any two states as basis states as long as they meet certain requirements. And we can, it just follows the same progress there, or process there. Yeah, there we go. We'll see it in the linear algebra section. Let's do an example. Let's do 2.10, pardon me. We've got 1/2 0 minus. If we're going to measure in the z basis, well, we know how to do that. We're already in the z basis, so we'll get we'll just take the norm squares of the amplitudes. We'll wind up with 1/4 and 3/4 respectively for state 0 and state 1. To write it in terms of plus and minus, we bring in what we know about. So using the plus minus basis, we'll simply substitute in what we know for those to equal here plus, oh, pardon me, minus 3 1 square root of 2 minus. Alright, so we'll do the full distribution and grouping here for this example. So we wind up with 1 over 2 square roots of 2 I plus minus I minus square root of 3, 2 over 2 square roots of 2 plus minus minus. Work our way through things here. We wind up with 1 over 2 square roots of 2 plus state plus 1 over 2 square roots of 2 in the minus state minus square root of 3, 2 square roots of 2 in the plus state minus 3, so pardon me, square root of 3 over 2 square roots of 2 in the minus state. So get them figured out here. We wind up with, so grouping our like terms, our plus states and our minus states, we wind up with 1 minus square root of 3 over 2 square roots of 2 plus, and for the minus state, we wind up with plus 1 minus square roots of 3, 2 square roots of 2. Okay, so that's part B, writing the qubit state in terms of plus and minus. Now, once we measure in plus and minus, what do we get? Well, norm square everything. Norm square. Hang on. I did not carry something through properly. Good times. That's right. Because that becomes plus, which means this becomes plus. All right. Small mistakes, right? They all add up. All right. Norm squared. We would take the complex conjugate, but in that case, it doesn't exist. So we'll just do which is 1 plus minus square root of 3 minus square root of 3 plus 3 over 4 times 2 is 8. So get over here. Gives us 1 plus 3 plus square root of 3 plus square root of 3. Can I move this with this? Ah, beautiful. What's going on here? Okay. Where this thing went. Why is it not showing it? Okay. There we go. Over 8. So we wind up with 4 minus 2 square root of 3 over 8. 4 plus, excuse me, and 4 plus 2 square roots of 3 over 8, 4 minus. Let me just verify that in the solutions section, 2.10. We pull out the 2. Sorry, we pull out a 2 here. So we wind up with 2 minus square root of 3 over 4. And 2 plus square root of 3 over 4 in our final form. Yep. So, and that equates to 0.07 roughly and 0.93. All right. Consecutive measurements. So every time we measure, we are collapsing to a given state. However, we can get around that by measuring in different bases for consecutive measurements. So for example, in this, what it's talking about, 2.3.4, let's say we measure first in the z basis. We measure in 0 or 1, so it's going to collapse to 0 or 1. So since if we measure the second time in the x basis, then it'll collapse to plus or minus, and 0 and 1 are halfway. Excuse me, 0 and 1 are halfway in between. Let's see if they have that block sphere. So 0 and 1 are halfway in between plus and minus, here and here at the poles, right? So they will collapse with equal probability to plus or minus. Now we've got one that's in plus or minus. Plus and minus are halfway in between 0 and 1. So if we measure in the z basis again, we now have a 50% chance for each to go back to either, if you can read this absolute Sanskrit, to either 0 or 1. So, for example, exercise 2.12, a cubit is in the state 0. If you measure it in the x basis plus or minus, and then measure it again in the z basis 0 or 1, what is the probability of getting 0 or 1? Well, we just discussed that, so if we are here, we're at 0, we want to measure in the plus or minus. With 50% probability, it'll go to plus, 50% probability it'll go to minus. And then once again, if we measure, so either go in here or here, and then there's a 50% chance of it going from here when we measure back in the z basis back to 0 or to 1. So the back to 0 or back to 1. So the fact that there's multiple transformations does not change the probability. It's basically, we're just concerned about the probability right before it's about to switch. It's not asking about the sequence. It's asking about, so it's just half. So A is 0.5 and B is 0.5 here. All right, cool. So learning where the point is on the block sphere. So as I said earlier, when you multiply by a global phase, it does not change the amplitudes. It does not change the probabilities of being in either state. So for example, here we have EI theta. Even if we multiply this in, once we take the norm square of these amplitudes, we're taking this will get distributed through, right? We'll be taking this and multiplying it by its complex conjugate. So E I theta multiplied by E negative I theta, which just equates to E0, which is 1, right? So the phase is not going to affect our amplitude. It's just basically, but it can be used to shift the location of a point. If this is based on the previous example they had earlier. So if you're measuring it in the x basis, so you would take this, plug in what you know about the 0 and 1 equivalencies states in the plus and minus basis, and then calculate that out. That's what we showed earlier. Then the probabilities are once again unaffected by the global phase. Global phases are physically irrelevant. A relative phase is physically significant, though. So if we apply the if we apply something very specific like EI to the pi divided by 2, that will alter. So let's take a look at an example, just to clarify my mind on this. This is the first time I've seen some of this stuff since what's going on here? Okay, man. We have like a million whiteboards active. Okay. Is there a measurement that can distinguish the following pairs of states? If yes, give a measurement. If no, explain your reasoning. So we know that a global phase is irrelevant. Is irrelevant. Okay. So for in example A, we have the same state. We have plus, except we just apply a global phase of EI to the. So the global phase should not impact the measurements. It shouldn't alter the amplitudes. 1, 3. Yes, they differ. The two states differ by global phase, and are. Oh, I'm trying to write with the wrong end of the pen. Equivalent. Equivalent. In B, well, these are literally two different states, right? We have they differ by we have 0 plus 1, 0 minus 1. So that is, what is it, the relative phase, pardon me. So they differ by a relative phase. And we can measure in the plus minus basis, and that'll actually be able to distinguish the two states. This, again, it's the same thing with the global phase. So they differ by a global phase, and therefore they are equivalent. Spherical coordinates. All right. For Christ's sake. What is this? No, go. Alright, whatever. We'll leave that triangular device there. Alright, so generic quantum state represented with psi. You get to see me butcher some Greek letters now. And it's written as this ket. So generic ket is represented as alpha, this beta, and it's normalized. So the norm squares of alpha and beta are 1. So to determine the location of this, so A is real and positive. Beta can be complex. So alpha is going to equal the cosine, and beta will be equal to E I cannot remember what this thing is called. Rho sine of theta over 2. So we can therefore rewrite our psi ket in terms of this parameterized here. So cosine of theta over 2 stays 0. Whatever that thing is, sine 2, 1. So we'll follow along with this example that they're continuing here. So we've got psi equals 3 plus I square root of 3 for 4. 0 minus 1/2 state 1. So the amplitude of state 0 is complex, but it needs to be real. So to make it real, we must first convert it into its polar form by what we learned earlier. We wind up with square root of 3 over 2 ei pi over 6 minus 1/2 1. Now we need to pull out this ei to the pi over 6 in order to make this real. This part here, this amplitude. So we wind up with ei to the pi over 6 square root of 3 over 2 state 0 minus. So when we multiply this times whatever we're going to place here, right? Because we have 1/2 1. We're pulling it out. We know that it needs to equal 1. Well, we know from earlier that this multiplied by its complex conjugate equals 1. So we'll just write its complex conjugate here. So e negative I pi over 6. And now we have real, positive, complex, and these states are equivalent because we have this global phase, right? So the global phase is irrelevant. So when these are equivalent. Okay. We still need to change the minus sign to a plus sign. This part tripped me up a little bit when I was going through this. I didn't really get why they were using this ei negative 1. Is that how it evaluates? I didn't actually check the numbers. But we can factor out, basically what they're saying is that this minus 1 is equivalent to here. So then we simply can pull that out. And we wind up with plus e minus I pi over 6 1/2 1. Oh, okay. And we wind up with square root of 3 over 2 0 plus e pi 5 to the 6th. It's this part here evaluated. We combine these. 6 1/2 1. So now we're going to take the form of equation 2.8. Right, we're trying to get into this form here. So we know that cosine of theta over 2 is equal to square root of 3 over 2. And we know that e of I, this is equal to e of I 5 pi over 6. Right. Because beta is equal to that. Okay, I'm going to refresh. And sine of pi over 2 equals 1/2. Excuse me. So we solve, right? We're going to try to solve to figure out what gets us here, right? So we solve for theta, and theta is equal to pi over 3, and this guy, 5 pi over 6. Now we can just take this, plug it in. By 2 ei 5 pi over 6 sine of pi, Jesus, over 3 divided by 2. One. All right, so now we have our spherical form, and we can take this and we can map it in here to our block sphere using the theta is the polar angle, whatever this one, rho, again, no idea, angle across the x-plane from the xy plane, the azimuthal angle. We can do an example on this if you guys want to. I'm going to move on. You know what? Damn it. Let's. All right, I'm starting a new whiteboard, and let's just. Lakshmi, or the head TA, you know, she did advise the more problems you can work through in the book, the better, right? That was her approach. Obviously, it worked for her because she made an A in the class. To be a TA, you have to make an A. So let's take a look at 2.14. We won't sketch it, but let's calculate this. Let's calculate theta and rho. So we're in the state plus I. Luckily, we don't have to mess around with doing any kind of complex conversions. So let's turn this around. Spherical coordinates. So beta 1. That looks horrendous. All right. So let's distribute things through. We know that this, actually I did not work through this example last time, so we're probably going to have to figure this one out together. So alpha is equal to cosine of theta over 2. So 1 over square root of 2 equals cosine of theta over 2. And equals E I rho sine of theta over 2. All right, that's interesting. So, well, we can solve for theta easily. Theta over 2. We pull up Desmos. All right, so there we go. Inverse of, what was it? 1 over, oh, it's not, it's cosine inverse, sorry. Cosine inverse of 1 divided by the square root of 2. Okay. Nope. I've never used this before. All right. Equals 45. So we know that theta divided by 2 is 45. So cosine of 45 degrees gives us 1 over square root of 2. And that way theta is equal to 90 degrees. So, bam. Sine of 45 EI rho equals I over square root of 2. Okay. And in nomics CS1, I'm not sure. Honestly, I'm not sure if the math midterm is going to go this deep on the math side of things. I'm just like a better safe than sorry kind of person. We've got all week, and honestly, understanding this is going to help understand, as things get more advanced, we can understand the mathematical underpinnings. That's just my take on it. I feel the most confident when I understand as much as possible. So to solve for rho, with the previous example that they used, we wound up with e I to the theta. I'm kind of lost. So let's just do real quick. Let's do sine of 45. Oh, that's not it. I really should remember my unit circle by this point. Square root of 2 over 2. All right. So we've got I over square root of 2 equals EI times square root of 2 over 2. Is that right? Yes. All right. I'm just going to do this algebraically. So let's divide it by square root of 2 over 2. That gives us 2I over 2. That gives us I equals EI to the rho. Now, where does that take us? Any thoughts, guys? With the other one, it was a bit more straightforward because we had the complex component in there already that had like e raised to the powers. I'm going to bookmark this one to come back and touch on. I'm just going to move on from this one. I want to get into some. What is this? 2.14. Let me bookmark this in my physical textbook. All right. Cartesian coordinates. This one weirded me out a little bit as well. Just because understanding, like once we have the angles, the theta and the rho here, I didn't really understand what they were trying to get across here with also, I apologize, this is also public, so there could be some bots or scammers dropping in here from time to time. Not sure. So we have our XY. We have our angles, right? We have these guys here, and this determines how far out we're coming. Okay, where are my notes for this? I forgot. I have literally handwritten notes on this entire section. Okay, so okay, so x is equal to the sine theta of multiplied by cosine rho. Y is equal. This threw me off just a little bit here. Why is it? If anyone with a bit more of a strength in trigonometry can chime in about what causes this. Not really certain why these sides are those values. The opposite side is equal to the hypotenuse times sine rho, or sine is equal to the hypotenuse times. Moving on. I'm not going to waste any brain power on this one. Physical qubits, I'm skipping this section. I don't think there's anything we need to worry about. Now for the meat. Now for the steak portion of the dinner. Quantum gates. The good stuff. The start of the good stuff. Or the start of the bad stuff, depending on how you feel about it. So, and real quick, let me just see. Are we moving into linear algebra after gates? Yeah. Perfect. All right. The good old quantum gates. Let's get a fresh canvas for this bad boy. Beautiful. So simply put, as it says right there, quantum gate U transforms the state. Transforms the state of a qubit into other states. Qubits, and this is like the easiest conceptual thing that I've seen on looking at other stuff online, is that qubits rotate, or pardon me, qubits are rotated by gates. They affect some type of transformation onto the states of the qubit. So looking at this example, this is a very general example here. So let's say we have just our basic form here. Then that is, let's just forget that for a second. Of 1. And it distributes through and directly affects the state. So if the effect of U on state 0 is that it creates this superposition, then that's what we wind up with, right? And factoring in also the previous amplitude. So gates rotate qubits into different positions, affecting the amplitudes. Unless you're the identity gate, in which you don't change anything. We'll get there in a second. And so a quantum gate also, as they show in this example, just going through this algebraically, taking the norm square of these amplitudes that result from applying this U gate to this kind of arbitrary example state that they have here. The quantum gates keep total probability t to 1. They don't affect the validity of a quantum state, right? So they keep it, they maintain normalization. Sorry, that's the best way to put that. Honestly, this stuff really makes sense to me more as matrices. So that's where it really clicked for me in the next section when they start looking at gates as matrix operations. But we can continue to go through. So let's just real quick, let's look at one of these examples. So if we apply U to state 0 and we wind up with +1. If we apply it to state 1, we wind up with 0 minus 1. So let's say, it says here, say that alpha state 0 plus beta state 1 is a normalized quantum state. It's equal to 1. Let's apply U to that state psi, and we wind up with is alpha of 0 plus 1 plus beta 0 minus 1. For me, our answer to A is U a valid quantum gate. Well, did we change the amplitudes? Let's take a look. state 1, we wind up with alpha plus beta, state 0, alpha or plus alpha minus beta, state 1. So if alpha and beta are normalized already, then the effect should be good to, oh, sorry, this is 2.22. Sorry, just checking the, I see. So no, this is not a valid quantum gate. As the is so this is equal to 2. So if we norm square these, we get and a minus beta squared. We know that this equals 1. It's a squared plus b squared equals 1. That makes any sense. Sorry. Mentally working through this right now. A squared plus alpha beta plus beta squared. We get alpha squared plus beta squared plus 2 alpha beta. That's 1 plus 2 alpha beta. Regardless, I'm not going to go. I think I'm going down the wrong path here with this algebraic stuff. But we know that this is equivalent to 1. We know that b times its complex conjugate. Basically, the probability is 2. Also, just a heads up, I don't know if you guys have tried Notebook LM, but I used it in KBAI. We're allowed to use that for our notes, and we can even use it on the exam, etc. But it is fantastic. You can feed it this textbook and ask it to tell you all kinds of things about various concepts and various problems. I'm going to have to earmark this one, 2.23, for an LM session. Ask it what it thinks. 2.23. Alright, so classic reversible gates. Alright. So let's say that we have a NOT gate, right? A classical kind of NOT gate that always flips the bit. 0 to 1, 1 to 0. Let's say that we have a qubit that is in state 0. We apply this NOT gate. We'll use U for the generic there. That'll flip it into state 1. Same thing, if it's in state 1, it'll flip it into state 0. Therefore, if we're acting on a superposition, this NOT gate, this U gate, which is a NOT gate, will have the effect of we distribute that through. It's going to go affect the states. Which turns into of 0. And basically, we have flipped the amplitudes. The final states are also still normalized. So up here, we had this normalized. This state was already normalized. Alpha squared plus beta squared equals 1. It's still normalized. Therefore, this U gate that reverses, that's reverse. U reverse is it's a valid quantum gate. So classic reversible logic gates are valid quantum gates. They just switch around. In this one, we just switched around the amplitude. So any classical reversible logic gate, just kind of moves the amplitudes around. So we can see, for example, we have this gate that's irreversible. So this is an always 0 gate, and it no longer is normalized after we apply the gate, because we wind up with alpha plus beta state 0, which does not equate 1. All right, let's take a look at some of these truth table examples, and just all right. So let's take a look at this guy. This should look familiar to you guys. It is just an identity, right? So it just spits out the same thing. Is it reversible? Yes. So therefore, it is also a valid quantum gate. It doesn't change the amplitudes at all. So if we had alpha of 0 plus that's alpha plus beta of 1, and we applied this identity gate, let's just call it that, right? It's just going to wind up equaling this, right? It doesn't change anything once we apply the gates to each of the individual states. This guy, so B is an always 1 gate. 0, 1 maps to 1 and 1 regardless. We know that this is not reversible. Given the outputs, how are we going to tell what the inputs were? But just to prove this in terms of a ket, in terms of a superposition, let's just call this a always 1 AO gate. So AO. Let's apply that to a standard superposition. Well, we wind up with 1 plus beta of 1. So now it's a alpha plus beta 1. And when we take the norm square of alpha plus beta, it's not going to be the same as alpha squared plus beta squared. So similar to the example they showed with the always 0, which was not reversible, and also wound up collapsing everything, or not collapsing, but winding up being alpha plus beta state 0. This winds up alpha plus beta state 1. All right. I'm going to go AFK for 5 minutes. I'll be back at 8:17 Eastern. Just going to grab a quick snack. You guys do whatever you want. Also, really quick, as you can tell, this is pretty much the first time I've done anything like this. Very green, not a fantastic teacher. You're mainly listening to my musings as I'm in my thought process. So if there are any suggestions that you would like to suggest, any suggestions that you have that could improve this process, or like you feel like there are some different things that we could do to help make this more, frankly, um, interesting and entertaining, just let me know in the chat. I'm, as I said, first time doing this. Um, Normally study by myself, so in order to bridge the gap to the collective, I welcome any feedback. I will be back at 8:18 Eastern. All right, let's do it. Sorry about that. Ran a minute or two over. All right, common 1-qubit quantum gates. The identity, or I gate, preserves the state. So 0 just turns the same thing, basically. The poly X gate, or the NOT gate, turns a state of 0 into a state of 1, and vice versa. Once again, we can see that it's a rotation around the x-axis of 180 degrees. So again, gates just rotate. So we have a point here on our block sphere that's not even vaguely spherical. Say it's here. We're going to rotate it 180 degrees. Now it's here. And we have, oh, sorry, that's not right. That's a 0. Okay. We have flipped into the state. Flip the state, pardon me. Double X gate does nothing. It just returns us back to where we were. But we can generalize into, let's say we have an even number. Let's say we have an even number of X gates. Well, then we'll just wind up back where we started. If we have an odd number, they extrapolate that here. It's simply 500 double X gate. For example, with this 1001, I think there was a question like this on a problem set or a knowledge check. It's just 500 double rotations and then a single. So a double X returns us back to where we were, so it's equivalent to an identity. So you basically have 500 identity gates and then 1 X at the end, which just equals to an X. Okay. Poly Y gate. Turns state 0 into I state 1 and 1 into negative I state 0. That's, as it shows down here, that's just a rotation 180 degrees around the y-axis. Poly Z gate. Keeps 0 as 0. And turns state 1 into negative state 1. So as it states, this is not a classical gate at all. And it's a rotation around the z-axis of 180 degrees. And we'll prove this. We can do the exercise 2.28 to work through that. Okay, so looking at let's look at these two here. These are interesting to me. So looking at 217, 150, plus beta. This is this generic psi. Excuse me. So 217 Z gates and 101 X gates and 50 Y gates. Let me first, really quick. Okay. So we know that since these are 180 degree rotations, any pair of gates is just going to be equal to an identity. So Y50 is just equivalent to 25 I gates, identity gates. 101 X gates is equivalent to 50 I gates and 1 X gate. 217 Z gates is equivalent to 216 divided by 3, it's 108 and 1 Z gate. Obviously these are going to go away, so we're just left with the ZX on 0 plus beta 1. We apply innermost first, so we have Z of alpha X 0 plus beta X of state 1. The X gate flips the bit, right, or flips the state, so Z of alpha 1 plus beta of state 0. So we can rewrite here real quick before we do the Z. So beta of 0 plus alpha of 1. The Z gate keeps 0 as 0 and turns 1 into an amplitude of minus and a state of 1. So keeps 0 as 0. So the Z gate applied here we wind up with beta of 0 minus alpha of 1. Still completely valid. Once we take the norm squares of these amplitudes here, they'll still equate to 1. And let's take a look at, so 2.27 is of interest to me because we use it. It's discussed later in Grover's algorithm. I don't have, it doesn't look like I worked through that one. So let's take a look here. So prove that xz of generic psi there is equivalent to minus, okay. So let's take a look. Let's go through and apply these sequentially. So our generic psi, bam, And we're going to apply all these gates to that. So X, Z, X, Z onto this superposition. Or we know that Z keeps 0 as 0 and turns the amplitude for 1 minus. So once that is finished, we've got alpha of 0 minus beta of state 1. X flips, so amplitudes switch. So we get alpha of 1 minus beta of 0. Z keeps 0 as 0 and flips or negates the amplitude for 1. So we get minus alpha 1 minus beta of 0. And X flips the amplitudes once again. So we wind up with the new set, let's call this psi star after all the gates here, psi prime, if you will, is equivalent to minus beta, minus alpha 0, because in this last step we just flip the amplitudes, minus beta state 1. We want to show that this is equivalent to minus 1 multiplied by the original superposition. We pull out a negative 1, and voila. We have the original superposition just multiplied by negative 1. Similarly, we'll just smash through this real quick. This example with Z, X, Z, X. So we'll just take it. I'll just write it like this. So 1. So applying that X gate winds up with beta and alpha. Then applying the Z gate winds up with beta 0 minus alpha 1. The other X gate, we're just going to flip we're just going to flip those amplitudes. So minus alpha 0 plus beta 1. And the final Z gate, 0 stays the same. Beta gets negated. And we have the exact same state that we saw before. So minus 1 alpha 0 plus beta 1. So even though we applied these gates differently, so we did ZX, ZX, and before we applied XZ, XZ, we have equivalent results. So it really doesn't matter what order you apply the gates, as long as you apply the same gates in the same numbers during a sequence, we wind up with an equivalency. All right. S gate, or aka the phase gate. What is that? Phase. I don't know what's going on here. Okay. Excuse me. Phase gate, also known as the S gate. It's the square root of the Z gate, and it causes a 90-degree rotation around the Z axis. It takes 0 and leaves 0, because that's what the Z gate did as well. And S of 1 gives us I of 1. So S 2 times is equal to z. And s 4 times is equal to I. We're at a point, we go around 90 degrees, 90 degrees, 90 degrees, 90 degrees, boom, we're back. The t gate, the fourth root of the z gate, which is a 45-degree rotation around the z axis. So it's the fourth root of the z, or conversely, the square root of the s gate. It's a 45-degree rotation. So again, 0 gives us 0, and t of 1 gives us e raised to the power of I multiplied by pi 4, 1. So 45-degree rotation around the z-axis. Okay, so let's take a look at exercise 2.28 to kind of pull these things in together. So we have r sub z of theta, which rotates around the z-axis by an angle theta. It has the effect of, obviously it's going to leave 0 as 0 because all that the z-gate always does, and then theta sake. Okay, there we go. Of 1 equal to e I. So there's this phase, right? It's applying a phase there. So the z gate, s gate, and t gate are all specific instances of the RZ gate with, yeah. So z is when we're using pi. When theta is equal to pi, pardon me, or because e I, for Christ's sake, e I to the pi is -1, and so up here, for Christ's sake, here we saw that the z-gate turns beta negative, or applies a negative to the one state amplitude. So excuse me, it leaves 0 as 0, and then it applies this phase to the amplitude. So in the case of pi, in the case of the z-gate, it's using theta pi, so that's -1. So -1, state 1. Pi over 2, pi over 4, etc. So calculate r sub z of theta of psi. Okay. That is simply that results in alpha state 0 plus beta e I to the theta of 1. Show the total probability is 1. So RZ is a valid quantum gate. Okay, so we'll just do the norm squares. Alpha squared, and we know that beta e. Since this is complex, what we'll do is we'll take the and multiply it by its complex conjugate, which this, as we discussed earlier, it's not, this is squared within here. So this equates to 1. So we have beta squared times 1, beta squared. So we wind up with alpha squared plus beta squared equals 1. Excuse me. So it does not affect normalization. This R sub z gate, using a rotation angle around the x-axis, or the z-axis, pardon me. It does not affect amplitudes, the normalization of the amplitudes, so it is a valid quantum gate. And therefore, the Z, S, and T gates are all valid. All right, let's start on a new whiteboard here for the next gate sequence. Oh, the goat Hadamard. I don't know why it's so bold sometimes and it gets thinner, the writing. So let's take a look at the transformation for H. So turns state 0 into a superposition of 0 and 1, of an equal probability superposition of 0 and 1. And it turns state 1 into a also this is our plus state, also known as our plus state, and this is our minus state. Jesus. All right, gibberish here. All right. H is a rotation about the x plus z axis, which is the axis that lies in between the x and z axes. Interesting. So H maps from 0 to plus, as we saw, from 1 to minus, and also maps from I to minus I. And vice versa, right? So we can say, if we apply a Hadamard gate to the state I, it'll go to state 1. Excuse me. All right, so they just have some examples here of what happens when you apply the Hadamard gates to, so we have, for example, state I. It just winds up with, taking it to state minus I, just with a global phase. So essentially it's equivalent to state minus I. Okay, so let's take a look at Let's take a look at 2.29 in the textbook real quick, just to do a practice of applying a Hadamard gate to an arbitrary psi. So we have psi is equivalent to our alpha 0 plus beta 1. We're going to apply a Hadamard gate to psi. That's going to be equivalent to alpha Hadamard to state 0 plus beta Hadamard to state 1. Transforms 0 into plus and 1 into minus. So we wind up with alpha 1 over square root of 2 times state 0 plus state 1 plus beta of 1 over square root of 2 state 0 minus state 1. Let's pull out 1 over square root of 2 and combine like terms. So alpha 0 plus beta 0 plus alpha state 1 minus beta state 1. If I can move this over here. Perfect. Leads us to 1 over square root of 2 plus beta 0 plus alpha minus beta 1. So let's distribute. Actually, let's distribute this back in. Sorry. Alpha plus beta over square root of 2. Alpha minus beta over square root of 2. Let's verify. First off, let me make sure that that is the correct state. 2.29. 2.29. Yes. Okay. That is the correct state. Perfect. Now let's calculate the total probability to verify that they are normalized and therefore H is a valid quantum gate. So let's take the norm square of alpha plus beta over square root of 2, alpha minus beta over square root of 2. We wind up with interesting. So we wind up with that's what I thought. So if we're going to well, then in the norm square we would be multiplying by the complex conjugate. It's b squared. Let's proceed without that. So let's just do this algebraically. A squared plus 2 alpha beta plus beta squared over 4. And these will both be over 4, so we can just combine here. Plus alpha squared minus 2 alpha beta minus beta squared. Let's pull everything together here. So 2 alpha squared over 2, or pardon me, over 4. All right, I apologize. This is correct. This is the correct state. But then when I was calculating the total probability, that's where things got wonky. because oh, you know what? It's plus. So we have 2a squared plus 2b squared. Oh, over 2. Oh, Jesus Christ. Thanks, chat. Over 2. Because square root of 2 squared is 2, not 4. Jesus Christ. Georgia Tech grad student here. Over 2. So a squared plus b squared. Boom. Perfect. So when we take the norm squares, and we know that alpha and beta were normalized to begin with, therefore their squared equals 1. When we take the total probability of, we take the norm squares of the new probabilities based on the Hadamard gate, we still get 1. Perfect. H is a valid quantum gate. It does not mess with the normalization. All right, so we can combine quantum gates to create all sorts of states that we wish. Excuse me. Gates, as we saw earlier, are applied from right to left. So this H goes first, then the T, then the S, and the H. Every one transforms the amplitudes in some way, or doesn't, depending on the gate type, right? And so the resulting state that we wind up here is we were in state 0. Now we have been rotated to be, we were in state 0 with 1, right? And now we are in some different superposition. It's pretty straightforward. Let's take a look at 2.31 because we haven't used the T-gates yet in any examples. So Y51, H99, T36, Z25, on doing that on state 0. So as we'll recall from earlier, pairs of Y gates cancel out, and I believe, okay, yeah, 2 H gates as well, just verifying there. So 2 Y gates, 2 H gates, and 2 Z gates, in those pairs become identity gates. So we know that we have 51 here. That becomes that's 25 pairs of Y's. So we wind up with 25 I gates and just one. Just one Y gate left. We wind up with one H gate here as well, because otherwise we have 49 identity gates. T gates are a little bit different. They're 45 degrees, so it takes 8. Yeah, it takes 8 T gates to be an identity. So that means that, so we've got 36. 8 T gates is an identity. So we've got an identity and then 4 T gates. A T gate is a 45 degree rotation. That way, if we're applying a T gate 4 times, we are applying it 45 times 4 is 180 degrees. And what do you know? That's actually just a Z gate, right? A Z gate is 180 degree rotation around the Z axis. So we can just completely collapse this to a Z gate. So this is just equivalent to 1 Z gate. And then we have 25 Z gates here. So now we have a total of 26. We know that 2 pairs of Z gates are identity gates. So that leaves us with 13 pairs. So these do not exist, essentially. They have no effect. All of the entire second half, the T36 and Z25 gates, all basically equate to a single identity matrix, or identity gate, pardon me. So really, we just have to apply a Y gate and an H gate here to 0. So we know, so we'll start from the right and work our way to the left. So we know that H on 0 turns it into the plus state. So now we'll have Y 1 over square root of 2 state 0 plus state 1. And we're now applying a Y gate, good, a Y gate, where were we? Oh yeah, 0 to I1 and 1 to negative I0. Flips the bits and applies a plus and a minus. Where were we? Okay. So we wind up with one over square root of 2 to I of Jesus. Yes. So 0 becomes 1, and the amplitude is multiplied by I. And 1 becomes 0, and the amplitude is multiplied by negative I. 0 becomes 1. What is this? And 1 becomes 0, and the amplitude is multiplied by negative I. We rewrite this for concision. Double check the answer key. That is 2.31. Interesting. So they're showing me negative I on minus. Oh, that's because we can pull this out. Sorry, we can pull out a negative I, and then we'll have negative I 1 over square root of 2 state 0 minus state 1, which is equivalent to the minus state, and voila. Minus I, state I, or state minus. Cool. All right. 1-bit quantum gates are rotations on the Bloch sphere. I don't remember if I went over this little section here less. Okay, let's work through it. I don't think. No, I don't have this in my notes. Means I probably didn't really look over this section. So, okay, so basically this is just showing that rotation preserves Um, that this is just showing that rotation is linear, and it also preserves the total probability. I don't think this is necessarily. This is pretty dense. If this is something you guys want to come back to, we can always do that. I'm going to move on from this. We'll move into quantum circuits. Looks like we got about an hour left on today's session. So let's move into this. I don't know why I'm missing. Where did all this go? Definitely went through these sections. Where are they in my notes? Okay, whatever. We'll just take new notes. So circuits are read left to right. Oh, I think I skipped through most of this because, it's just a little section here. All right. Well, shit, we made it through section 2, or chapter 2. Was there anything in this chapter you guys want to go back and touch on? Any example problems? Anything that didn't click? Anything that anyone's interested in revisiting? Excellent. All right, let's move on to a quick linear algebra review. So I talked to Lakshmi on Discord yesterday, and she said this plus like a tiny review on the eigen stuff, as I put it, is completely sufficient to handle everything in this course for the most part. In this, at least in what we're going to do. So we can just run through this really quick. I think let me see what I did for this. So, excuse me. But this linear algebra section is really where it started to click for me, because we can start thinking about things as matrices instead of, all right, so 136. Okay, so it's about a 20-page chapter. Well, we could bang this out. All right, so again, this is probably old hat for most of you guys. I mean, I have been, like yourselves, most classes, aside from like the really kind of more high-level stuff, require some use of linear algebra at some point, especially like RL, DL, some of the more machine learning heavy courses. I don't know if anyone here is doing that concentration, but there's a lot of linear algebra there. So I'm just going to run through this real quick, so we can move on to we can be primed to move on to multi-qubit stuff in tomorrow's 4 hours block. But it is useful to, especially in the bounds of quantum computing, to understand the notation. So state 0 and state 1 are both column vectors. 1, 0, 0, 1. So it represents 0 being on, 0. That's how I thought about it, at least. I really wanted to do 0, 1 at the start, because I was like, it's state 0, but it's 0, but it is state 0 is on, shall we say. So we can write our amplitudes as a column vector as well. They have a little thing there on 116 that shows that breakdown of alpha. So 0, same state 0 plus beta of state 1 in column vector form, and we wind up with 0 beta. It leads to that. We can write all superpositions can be written as vectors. Uh, for example, we've got this guy here in 3.1. That's just 1/2 square root of 3 over 2. There's a column vector form of that superposition. Applying, like translating from column vector to our probabilities. You see in 3.2. So we've got square root of 3 over 2 and 1/2 in column vector form. If we're going to measure it in 0, 1, what states can you get and what's the probability? Well, we can get 0 with 3/4, just the norm squares of those amplitudes, and 1/4 for state 1. Just translating from column vector into actual probability. Transpositions. Again, these are basic linear kind of things here, but A, alpha, beta. When we take the transpose of that, it's going to turn every column into a row. So beta. When we take the conjugate transpose, which comes in handy, so conjugate transpose of alpha, beta, and I just wind up doing like a tie, honestly, for that. So it's the transpose, but each we take the complex conjugate of each element after transposition. So that column vector becomes alpha, beta, but it's the complex conjugates of each of those. This is used so frequently in quantum mechanics that bracket notation has a special way of writing it. This is the bra. That could be confused with your brother, but we've got alpha and beta. So bracket notation. So this is equivalent to this, and then this is that. So we can go back and forth between these by taking the conjugate transposes. So conjugate transposition. So you can go back and forth between transposition by taking the conjugate transpose of whatever form you're in. If you're in the bra, conjugate transpose the ket, and the other way around as well. Flipping between kets and bras is called taking the dual. The dual of a ket is its bra version. All right. Here we're taking the complex conjugates of the amplitudes. It's pretty straightforward. Inner products. So let's say we are taking two states. Psi is alpha and beta, and whatever this one's called is Jesus. And so if we're going to multiply them, we're going to take their inner product. So we take our bra form of our psi, and we multiply it by our ket, the original ket for a row. So that equates to alpha, beta, the complex conjugates of those, multiplied by and we multiply out, and that's alpha plus conjugate times whatever that weird y thing is plus beta complex conjugate multiplied by this thing. And this is a scalar. So this just equals some number. We get an actual numerical result. So it's also a scalar product, since by the product of the two of psi and rho are a scalar product. Excuse me. All right. We can do a couple examples here if you guys want, but honestly, this is pretty straightforward. Actually, fuck it. Let's work through an example real quick, just to keep the home fires burning, you know. And we'll start a new whiteboard because I don't understand why it keeps drawing those lines, but okay. So for A, we want to find A, B, which denotes the inner product. Okay. So A in column vector form is 3 plus I square roots of 3 over 4 and 1/4. B is equal to, or sorry, not 1/4, 1/2. B is equal to 1/4 square root of 15 over 4. So we take the bra of A, which is the conjugate transpose. So we would have 3 minus I square root of 3 over 4, 1/2, multiplied by 1/4, and then the square root of 15 over 4. We do the dot product, so it's going to be 1/4 times this guy plus 1/2 times these guys here, which 1/2 times square root of 15. So we wind up with 3 minus I square root of 3 over 16 plus square root of 15 over, I don't know why I keep wanting to draw an 8 there, 15 over 8. We can factor this up here, so this is equal to 2 square roots of 15 over 16. We can combine now. So, all right. What is this? How does this make any sense, guys? And undo is doing nothing. Okay, we'll just work up here. So that leads us to 3 plus 2 square root of 15 minus I square root of 3 over 16. Let me double check in the text answers real quick. .4. Correct. Yes. 3 plus 2 square roots of 15 minus I square root of 3 over 16. And so to find the inner product of B and A, we could go through the whole process again. But they state here that if we find the inner product of psi and rho, then rho and the inner product of rho and psi is simply the complex conjugate of the inner product. So we can just say, okay, we've got AB here. Well, BA is just equivalent to the complex conjugate of AB. So we look at that. 3 plus 2 square root's 15. Oh, okay. 3 plus 2 square roots of 15 plus I square root of 3 over 16. Double checking here. Correct. So what is the relationship between your answers to parts A and part B? They are each other's complex conjugate. Okay, that's inner products covered. Orthonormality will come into play, with basis. So let's go ahead and dive into that. And put a new whiteboard. So several properties of the inner product. Oh, okay. So basically, if we take the inner product of a state with itself, it should equal 1. So if we have psi, then if the inner product of psi with psi equals 1, then psi is normalized. Because we wind up with, a squared plus b squared equals 1. Consider the inner product of the z basis states. So 0 and 1. So z is, so this is 0 and 1. So that's the conjugate transpose of, so 1, 0 times 0, 1. That just equates to 0. Oh, I see. Okay. So we look at the inner product of, plus and minus. 1 square root of 2. 1 over 1. It's our conjugate transpose of that. 1 over square root of 2. 1 and negative 1 equals to 1/2. 1 minus 1, which equals to 0. And then further, they look at basis state y. So basis states are orthogonal. So any two states on opposite sides of the block sphere have 0 inner product. They are orthogonal. So these two properties, normalized and orthogonal, can be combined into a single word, orthonormal. So 0 and 1 are orthonormal because each state is individually normalized and they are orthogonal to each other. And similar. So if we take two states and we find out that they're orthonormal in relation to each other, then we can use those as a basis, in other words. Okay, so just looking to see if there are any examples that we might want to work through here. All right, so looking at 3.6, just off the top of our head, we know that plus and minus are orthogonal, right? They're basis, they're normalized, and they are also on opposite sides of the block sphere. So they are orthogonal. 0 and plus are not. Plus represents the northern pole in regards to the x-axis, and then 0 is the northern pole for the z. So they are not on opposite sides of the block sphere. They're both normalized, but so they're not orthogonal. And then these two, we could take a look. So just visually inspecting 3.6c, we see that the amplitudes are switched and they're also complex conjugates of each other. Or are they? No. Let's work through that one. Actually, let's do 3.7. I didn't do that one on my first run through. So let's take a look at 3.7. So, all right. So find x so that a and b are orthogonal. So what does that mean? It means that their inner product is going to be 0. Oh, well, sorry. I apologize. I didn't see this. What's the difference between orthogonality and orthonormality? So orthogonal, it's right here. So orthogonal means that they have an inner product of 0. Orthonormality, it combines the two things. So orthonormal is they're orthogonal. So inner product of 0. And they are normal, which means that their amplitudes are normalized. So, like we were saying with plus and minus, when we take the inner product of these two states, as they show on 119 here, we get an inner product of 0. And furthermore, when we look at the amplitudes of each of these states, so plus has, 1 square root of 2, 0, 1. Minus has the same square root. So, 0 minus state 1. They both have normalized amplitudes. So they sum to 1. So orthonormal just means they're orthogonal and normalized. Orthogonal just means that they have an inner product of 0. Yeah, let's look at 3.7. Yes, norm square. Yeah, L2 normalized. So let's take a look at 3.7. So we have this ket A, which is in superposition 3 plus I square root of 3 over 4 plus 1/2 state 1. And, ket B, which is 1/4 0 plus x state 1. And they want us to find x so that A and B are orthogonal. Well, if they're orthogonal, we know that their inner product is 0. So we just simply need to solve for 0. So let's say we're going to find A and AB. We'll find the inner product of A and B. Then what that's going to wind up being is the complex conjugate, or the conjugate transpose, pardon me. So 3 minus I square root of 3 over 4, 1/2, multiplied by 1/4 x. All right. And so now we've got, we'll do the dot product, and we wind up with 3 minus I square root of 3 over 16 plus 1/2 x. Yes. And this needs to equal 0. And now we can just solve for x. So first, let me combine these into one ratio here. So 16, that's 8/16. That's 11 minus I square root of 3. So equals 0. So 11 minus I square root of 3. Oh, it's sorry. All right, I butchered this. Sorry, it's getting late. We got 30 minutes left. Okay, let me just erase. All right. Putting this into terms of 8, this is 8x over 16. So 3 minus 8x minus I square root of 3 over 16 equals 0. So multiply everything by 16, subtract the 3. So 3 minus 8x minus 3 equals 0. Subtract the 3. Sorry, 3, subtract the 3, and add the plus I square root of 3. Plus I square root of 3. So we wind up with minus 8x equals minus 3 plus I square root of 3. Whip it over here and divide by negative 8. We could pull a minus. We actually pull a minus out here to get rid of this. So x equals, we'll pull the minus out, 3 minus I squared of 3 cancels out the negative on the bottom, so 8. So x is equivalent to, so in order for these two states to be orthogonal, in order for the inner product to equal 0, in other words, they need to be on the opposite sides of the block sphere from each other. Then the amplitude x in state B needs to be 3 minus I squared root of 3 over 8. That's my hope, at least, right? Let's check it in the textbook. So 3.7. So they've got minus 3 plus I squared root of 3. Where did I go wrong? Oh, it's because it's plus. It's you add the 8x. You're not subtracting it. Okay, so this is not even having to pull out the negative is not even a concern. All right, oh, that's a minus. So yeah, it winds up being minus 3 plus I squared root of 3 over 8. So now that we know the x, right, we can say we need to find x so that b is normalized. So we know that in order to be normalized, the I see whenever I click, it keeps going and like, all right. Okay, we will just carve out some space here. So whenever we're normalizing, we need B, we need ket B to have a total probability of 1. So alpha is 1/4, beta is x. So we need to solve. So 1/4 squared plus beta squared, essentially, equals 1. That's 1/16. 15th plus beta squared equals 1. So beta squared is 15/16. Take the square root of that bad boy. You get square root of 15/4. Double check. Okay, so, and also one thing I was missing here was the phase. What are you doing, man? Theta. Yes. B has to be imaginary, has to have some imaginary, some complex component here. So we just put that in there in order to deal with whatever needs to happen. Because when we find our norm square, this will equate to 0 when we do the complex conjugate of itself. That just equates to 1. So for what values of x, if any, are a and b orthonormal? Well, the problem is that we found the value of x which made the states orthogonal, and we found the value that made them normalized, but those values aren't the same. And so there are no values for which for which a and b can be orthonormal, can be both orthogonal and normal. .8 looks interesting, but it also looks hella gnarly for this time of night. Okay. Projection, measurement, and change of basis. So inner products can be used to find the amplitudes of quantum states. This can be norm squared to yield measurement probabilities. Correct, we've looked at that before. So this psi with square root of 3/2 for 0 and 1/2 for 1 sits there on the Bloch sphere. It's more leaning towards the 0 pole, so therefore we have a higher probability. So 3/4 and 1/4 for when we measure in the z basis. So we can reproduce measurement using inner products. All right. So let's say we want to measure psi in the 0, 1 basis. So we can use the amplitudes. We're going to find the amplitudes using inner products and the orthonormality of the basis set ket 0, ket 1. So we can take the inner product, for example, of psi and the state and the state 0, and we wind up with the amplitude for amplitude alpha for state 0. Similarly, we can take the inner product of state 1 and the psi, and we wind up with the amplitude. The amplitude for state 1. We take the norm square of those, and we get 3/4 and 1/4. So this is equivalent. This is equivalent to. So let's say we have psi equals alpha 0. plus beta 1. We want to know the amplitude. So alpha is just equivalent to the inner product of 0 and psi. Beta is equivalent to the inner product of 1 and psi. Interesting. So we can find our amplitudes when we are measuring in different bases. So let's say we want to measure psi in the, let's say we want to measure this psi that we had up here with in the x basis. So we can take the inner product of plus we wind up with the inner product for some reason I don't have this in my notes. So let's just work through this. So that's equivalent to 1 over square root of 2 bra 0 plus bra ket, or bra 1, and our original psi with the various amplitudes that we have here. 1/2, 1. So we know that we know that we can distribute these through, and that becomes square root of 3 or 2 0 0 plus 1/2 1 1 plus square root of 3 over 2 1 0 plus 1/2 0 1. Simplifying, we know that the inner product of something with itself is just 1. So we wind, and the inner product of 0 and 1, as they are basis states, they're orthogonal to each other, is just 0. So we can equate that here. So these are 1, these are 0, they're gone, poof. We wind up with 1 over square root of 2, square root of 3 over 2 plus 1/2. Distributing square root of 3 over 2 square roots of 2 plus 1 over 2 square roots of 2. So square root of 3 plus 1 over 2 square roots of 2. So that's the amplitude of the probability that if we measure our psi in this original state in the x basis, that is the probability that we wind up in state plus. So similarly, we compute that with state 2, and I'm sure we could follow through here and do the total probabilities, make sure they're normalized. But yeah, it's useful because we don't know what the amplitudes actually are for for this measurement, right? We have the amplitudes for one basis, right? So it's in the z basis here, 0 and 1. And we need to know, well, what happens if we measure that? How's that going to alter the amplitudes if we measure it in a different basis? And we can use inner products to determine that. Just take the generic form here, 1 over square root of 2, take the kets, or take the bras, pardon me, and then distribute everything out, and voila. Okay. So now we know, so now we can effectively rewrite, if we have psi, we want to measure psi measured in x basis plus and minus. If we want to write that now, now we know that it's plus this amplitude here. So the inner product of the plus state and the psi state, state plus inner product of the minus state and psi, multiplied by the minus state. Now we transformed it just using linear algebra instead of having to do any type of rotations or anything like that. So for an orthonormal basis, so a basis is orthonormal, we can write the state of the qubit as alpha A plus beta B, where alpha is the inner product of A and psi, and beta is B and psi. Okay. Do you guys feel okay with that? Do you want to? Do you want to run through an example, or do you guys feel all right with that? All right. I'm just gonna move on. Let's take a look here at 3.3. And we don't... What time is it? Okay, we got 16 minutes before I was going to end the stream. I don't really want to dig into quantum gates just yet. I think I'm going to save that to start off tomorrow. It's a great starting point. Let's just round the last 15 minutes out with a work through of one of these problems, just to really drive it home, right? So, okay, let's take a look at let's take a look at 3.1 or 3.11. All right, so we have a qubit in superposition, and they give it to this. They give that. Pardon me. They give this to us in a column vector format. So let's say psi equals 1 square root of 6 and 1 minus 2i over 1. Oh, not over 1, but So express this state in the plus minus basis. Well, we know that we can express this as 1 minus 2i over square root of 6, 0. They didn't really tell us what state it was in, right? Plus 1 square root of 6, state 1. And to measure in another. Actually, I'm wondering now if we should. Traditionally, this should be real, right? I'm wondering if I should bring in some of the stuff we looked at in chapter 2, to make that real. Take a look here. I'm not going to worry about it. So we've got these two states. We know that if we want to measure it in, if we measure in the basis states plus minus, so plus is 1/2, or pardon me, 1 square root of 2, and we'll just bring it in like so, like they were doing in the previous example. So this is all for so if we want to measure psi in terms of plus, we know that the amplitude, the probability of getting plus, is what is going on here? Can I not click this thing for the love of God? All right. Is the inner product of plus and psi. That gives us the amplitude for being the probability, shall we say. So 1 over square root of 2 bra 0 plus bra 1 multiplied by the 1 minus 2i over square root of 6, 1 over square root of 6. Hang on. Oh, I see. Yes. Okay. Multiplied by 1 minus 2i over square root of 6, 0, plus 1 over square root of 6, 1. So then we'll just follow what we were doing earlier, where we were distributing. So we've got 1 over square root of 2, and we've got, as we go through though, we can just reduce because we don't need to take up all the space. So we know, so 0, so bra 0, cat 0, 1. So 1 minus 2i over square root of 6. 0 times 1, or bra 0 times cat 1, that equals 1. Or, sorry, that equals 0. So that's gone. 0, 0, 1 times 0, we know that that's 0, so that part's gone when we distribute it to here. And we bring it over to here, we know it's 1, so plus 1 over square root of 6. We can combine this stuff here. So 2 minus 2I over square root of 6 times 1 over square root of 2. It's okay. So there's 2I. And for the life of me, the square root rules are, so we'll just say oh, okay, that's right. Yeah. Square root of 12. Jesus. So that gives us 2 square roots of 6. We can pull out a 2 here. We've got 1 minus I over square root of 6. Okay. Verifying. That's number 3.11. Yes. 1 minus I over square root of 3. Square root of 3. Oh, that's right. It's not 2 square roots of 6. It's 2. It's 4 times 3. 2. Yeah, sorry. It's square root of 3. It's 2 times 2 times 3. All right. So 1 minus I over square root of 3, and then similarly, to find it in the plus, or to find it in the minus, we would just follow the same thing. So we've got 1 over square root of 2, 0 minus square root of 1, 1 minus 2I over square root of 6, 0 plus 1 over square root of 6, 1. Bring things through. Uh, 1 minus 2I over square root of 6. Yeah, everything else cancels out except for 1 over square root of 6 multiplied by the inner product of 1 and 1 minus 2I over square root of 6 multiplied by the inner product of 0 and 0. So we've got minus 1 over square root of 6. So square root of 2 minus 2I over square root of 6 minus 2I over square root of 12, which is 2 square roots of 3, which gives us minus I over square root of 3. Verifying. That's 3.11. That is correct. So now we have discovered the amplitudes of psi once we measure it in the plus minus. So plus minus, so minus I over square root of 3, and this one was 1 minus I of 3. I mean, we could verify, you know, as one final step. We've got like a minute left. We'll just take these and do a quick L2 norms here. Multiply them by their complex conjugates. 1 minus I plus, or times 1 plus I over 3. Negative I minus I is negative I squared, which is negative 1, so that's 1/3. And this equates to 1 minus negative I, which is 2/3. So it's just 2, and that gives us 2/3. Perfect. All right, everyone. Thank you for listening to what has certainly been a less organized and insightful session than I would wish. We'll reconvene tomorrow. In the meantime, hit me with suggestions. We'll make this second stream a lot better.